to be educated by Eduardo from an early age. So that's the oldest picture I have with Eduardo from a graduation ceremony where he was the Masters of Ceremony. And I first met Eduardo when I was an undergrad in Campinas. And I remember the day he first explained to me what strongly correlated systems were. And I thought that was very cool and decided that's what I wanted to do. And to do whatever Eduardo did. But unlike the organizers, I was never educated on disorder. For some reason, Eduardo chose to set me on a different path. So that's actually our first paper together, which was published around the same time, I think just a week apart from when this picture was taken. And that was published on the Revista Brasileira de Ensino de Física, which is like the Brazilian version of the American Journal of Physics. So it's just a very simple introduction to quantum field theory. And also, I was very lucky that when I was starting my master's with Eduardo, he actually taught a course at the Brazilian School on Statistical Mechanics in São Carlos, which was an introduction to bosonization. And this is the praise for Eduardo's lecture notes, which were published on the Brazilian Journal of Physics a year later, highly pedagogical, which they really were. And for me, personally, that was extremely useful because during my master's, we did some work on Lagrangian liquids from different perspectives, like impurities and magnetic domain walls and the one-dimensional Kondo lattice. And after that, I left for my PhD in Canada, but we kept in touch. We've been collaborating over the years. And quite often I find that even when we are not collaborating, the way I think about the problems and the contributions I can give are still very much influenced by the things I learned from Eduardo. So this talk is going to be an example of that. It's probably not very clear from the title, but I promise you see the connection eventually. So here's my outline. So I'm going to start with an introduction talking about topological phases with boundaries. And that will be useful for analogies with boundary of Fracton models that I'm going to talk about later. So I'm going to say a few words about fractons and then focus on the Chamon model as our example and try to understand different boundary phases of the Chamon model. Chamon here is, of course, Claudio, our previous speaker. And then I'm going to talk about how we understand these boundary phases in terms of ineffective field theory. And this work is done in collaboration with Wesley Fontana, who is a postdoc in Natal. He's our local expert on this stuff. And okay, so I'm going to talk about topological phases in the same sense that Claudio talked about before. So these are phases that have topological order. They're topological even if you break all symmetries, even like U1 symmetries like charge conservations. And the examples here are usually the fractional quantum Hall states or quantum spin liquids. And these phases have come with a lot of very interesting physics, like long-range entanglement. They have a ground state degeneracy that, as Claudio explained, have to do with these non-local operators that wind around the geometry in real space, like a torus that has some non-trivial topology. And the elementary excitations are fractionalized in the sense that local operators create at least pairs of these particles, and these particles have anyonic statistics. And then what we want to talk about is what happens when you put these topological phases on geometries with open boundaries and things that can happen at these boundaries. And in the case of two-dimensional topological phases, there's actually a very general classification in terms of the types of boundaries are classified by what is called the Lagrangian subgroups. Basically, the rule is that you have to look at your set of particles that you have in the bulk, your anyons, and select those which have bosonic self-statistics, which means you exchange them, and then the wave function is invariant under exchange. And also you group them by sets of particles that have mutual trivial statistics. So those are your subgroups, and then you associate one boundary with each of these groups of particles, and what they represent physically is that then it might be possible to create these particles in pairs in the bulk, bring to the boundary, and then condense these particles or not, depending on the type of boundary that you have. And of course, I'm going to use the simplest example here, which is Z2 topological order, which is the one which is present in Anderson's resonating valence bond state, the Z2 spin liquid. And by the way, there's another important anniversary this year, which is 50 years of Anderson's RVB paper. And as Claudio already mentioned, this kind of Z2 spin liquid found recent realizations in different quantum simulation platforms like the Google quantum computer, Rydberg atoms, and there's also ion traps from the Quantinuum quantum computer. And I'm really glad that Claudio already explained the toric code, so I can just flash this. So just to remind you of the basics, the toric code is, I'm going to use it as an example of Z2 topological order. It's a stabilizer code, so it's defined in terms of these operators that act on 4 spins. You have stars and plaquette operators. This is the Hamiltonian, and then you can create excitations in the bulk of a toric code by applying spin operators along strings. Like you apply a string of sigma z, you separate 2 types of particles, which are called the E particles, that are associated, where the energy is associated with the stars. But if you apply sigma x operator along a string, you can separate 2 particles at the ends of the open strings, which are the M particles. If, E here is for like electric and magnetic charge. And there's a third anion here, which is just the bound state of E and M, but that one is a fermion, so it doesn't count for the kind of condensation at the classification of the boundaries that I'm going to talk about. But you have here 2 types of particles that have bosonic self-statistics and some non-trivial mutual statistics. They're actually mutual semions. And then the question is, what happens if you have open boundaries? So now I'm going to put the toric code on a surface and cut the system somehow. And there are essentially 2 ways to do this. And these are known as the surface codes. If you imagine, I can cut the toric code like this. It depends on whether I break stars or plaquettes in this process. So for instance, there is this so-called rough edge here, where I have the stars are still okay, made of 4 sides, but I have to break the plaquettes. And then you have this kind of boundary stabilizer, which involves the product of sigma z on 3 sides only. It's like the broken plaquettes. On the other hand, if I remove this layer of sides here, I get a smooth edge, where now it's the other way around. You actually break the stars. So you have to define this boundary stabilizer as the product of 3 sigma x operators here along the edge. And what happens here is very simple if you think in terms of the excitations you create in the bulk and bring to the boundary. So now you can have the E particles and the M particles on the rough edge. Oops. On the rough edge, I can bring a star by applying the string operator. I bring it all the way to the edge, and then notice there is here another site. And if I apply a sigma z operator there, I can actually annihilate this star, this E particle. So the E particles condense on the rough edge. But if I try to do the same with the M particle, then it does not condense because I don't have another side to push it away here and annihilate this excitation. What I can do is only apply a sigma x operators here that will make this excitation move along the edge, but it cannot condense, right? And then on the smooth edge, it's the other way around. The M particles condense, but the E particles don't. So it's just to give you an idea of how we can classify these boundaries in terms of the anions and their condensation at the boundaries. So now we want to ask similar questions about Fracton phases. What happens if you have open boundaries of Fracton models? And Fracton models, they appeared, or actually the first paper here is due to Claudio. That was the first exactly solvable model that has this kind of physics that we now call Fracton topological order, quote unquote. And it's not really topological because you do have some ingredients of topological order in 2 dimensions, but also there is some dependence on the geometry. So for one thing, one important property is that these Fracton models, they have some restricted mobility. So you can create excitations in the bulk, but either they cannot move at all by themselves, or they can move by forming bound states, and then when they do, they only move along some very rigid directions on the lattice. And this gives a distinction between type 1 and type 2 Fracton models. So for this talk, I'm going to focus on Claudio's model, which is a type 1 Fracton model. And another important property here is that this kind of model that you define on the lattice, they have some ground state degeneracy that depends not only on the topology of space, but also on some geometric data. It usually depends with in a way that the degeneracy grows exponentially with a linear scale of the linear size of the system. So I'm going to give an example in the next slide. And also, it's also important to say that from the point of view of effective field theories, Fracton phases have been very interesting because they challenge a lot of the concepts that we're used to in quantum field theory. So, for instance, we know that this cannot be described by topological quantum field theories exactly because there must be some geometry dependence. And also, people have worked out some effective field theories for fractal models, but they suffer from this problem which is known as UV-IR mixing, which means that the effective field theory that's supposed to describe the low energy physics depends a lot on microscopic details that comes from the high energy physics. You can still write some effective action, which looks nice, but when you try to compute physical things like correlations and talk about degeneracy, the lattice scale keeps coming back to haunt you. I'm going to give some examples here. So, for instance, you can already see that when I say the ground state degeneracy grows with the system size, you have to count the degeneracy in terms of size divided by lattice spacing, right? So it's already something that will depend on the details of the lattice, which does not happen in the usual 2D topological. Mm-hmm. So this is a fundamental for there are models which cannot be coarse-grained. Mm-hmm. I don't know if this is related to that, or is this something completely different? Yeah, coarse graining here can be an issue. People have been talking about that. Like, it really depends on how you take the continuum limit. You might end up in different theories, or so many of these ideas break down in this kind of model. And also, this kind of, they're exactly solvable models on the lattice that have Fracton topological order, like Claudio's model, which I'm going to focus on. But they all involve multi-spin interactions, and as Claudio already explained, those are hard to come by in nature. And the proposals here is for how to realize them involve this kind of perturbation theory in some couplings to generate effective Hamiltonians. For instance, on the day you have Majorana zero modes, we could couple them in a way that you generate these 4-spin interactions. And then there are those proposals that are more along the lines of preparing states with Fracton topological order in quantum circuits where you combine unitary time evolution with measurements. So here's the Chamon model. It's also a stabilizer code. So it's defined in terms of, these are the stabilizers. They're now products of 6 spins, 6-spin operators. And you do like this. You take 6 sites along at the edges, at the vertices of an octahedron. So you have x, y, and z directions. And you put sigma x operators, 1 and 2, which are along the x-axis, sigma y along the y-axis, and sigma z along the z-axis. So you can check that this is really a stabilizer code in the sense that the operator is square to 1. They all commute with each other. The Hamiltonian is the sum of commuting can be written as the sum of commuting projectors. And this is just one stabilizer on the octahedron, but then you form an FCC lattice of, you can view the FCC lattice as a lattice of edge-sharing octahedra. So the operators on different octahedra commute among themselves. Something which is quite often confusing to me is actually there are two FCC lattices here. So the black dots here are going to represent the sites where the spins live, but you can also focus on the positions of each octahedron. And these I'm going to paint in colors because it was already pointed out in Claudio's paper that you actually have some global Z2 constraints, but one for each of the 4 sublattices of the FCC lattices. If you take the products of these octahedral operators on all octahedra that belong to the same sublattice, which are painted by the same color here, the product has to be equal to 1. And that poses a constraint on the kinds of excitations that you can create in the bulk of the Chamon model. So starting with some bulk properties, so for instance, it has been shown that this model has this kind of ground state degeneracy on a 3 torus, meaning periodic boundary conditions in all 3 directions. And it has a very funny dependence on the dimensions here. So if you take this the 3 torus with Lx, Ly, and Lz in each direction, the ground state sector is defined by this condition that the ground states have to be eigenstates of each stabilizer. And you can count how many of those you get, and the number grows exponentially with this n, which is given by the greatest common denominator between Lx over 2, Ly over 2, and Lz over 2. These lengths are defined in a way that they're always even, so these are integers. So you see this can vary very wildly with the dimensions here. The largest ground state degeneracy here would be when these are all equal, and then you can see that this would be just L over 2, and the degeneracy grows exponentially with the linear size of the system. So that's the ground state manifold, and if you want to talk about excitations, I'm going to call these defects, the condition that the eigenvalue of this stabilizer is now equals to -1, violating the condition for this ground state manifold. And you can ask what happens when you actually apply a spin operator on top of this ground state. Now, because of those constraints, you end up creating, in this case, I think I apply a sigma x operator here. It depends on what you do. It depends on the plane and the spin operator. But it creates 4 defects, which are contained on the same plane. Once you create these 4 defects, marked by the stars here, you can actually try and move the defects. But what you can do is only apply more spin operators along the line in a way that you separate the ends of this ribbon-like structure, and the defects where the energy, the excitation energy lives, are at the edges of this ribbon here. So now you see, now I have a pair of defects, which I'm going to call a dipole, that can move by forming this bound state, but only by propagating along these rigid directions, which are given by the face diagonals of the cubic lattice. So there's already some information about the lattice structure here that we have to carry over somehow to the effective field theory. And then you can also imagine what would happen if I had a single isolated defect. You can actually create this by acting with spin operators on a membrane, something which scales with the area. But say, if you assume you have only, now I'm looking at one single plane from the top, and imagine you have a single defect here, which I'm going to call a fracton. If you apply a spin operator here and try to move this single defect, you don't actually just move it, but remember, the spin operator creates 4 defects on the ground state. What I would do is to erase this one, which is already here, because this is a Z2 kind of theory, but create 3 defects. So you actually couple to this higher energy state, which has now 3 defects. And now that you have 3, you can single out this pair. This is a dipole, that I can send away if I want. And I have, again, just one single defect, which has moved from its initial position, but it can only do so by emitting dipoles or also absorbing dipoles if they're moving around. So the single defect would be immobile by itself. And then what we wanted to do is to ask what happens when you have a boundary in the Chamon model, and it's already known by study of other Fracton models like the X cube that the classification that I described for 2D topological phase is not going to work here. You cannot just classify gapped boundaries by the gradient in statistics in the bulk. And in this case, in the Chamon model, I have to cut the surface somewhere. I'm going to focus on 001 boundaries. And then when I do this, I break the octahedron, our stabilizers. I have to define a 5-side stabilizer like this. So I'm cutting along the z direction. So now it's missing one sigma z operator. And when I do this, now I actually violate 2 out of the 4 constraints for the 4 different sublattices that I mentioned before. And which ones we violate depends on where we cut the boundary. So for instance, now here, when I apply sigma x operator on this site, you create 2 defects on this green sublattice, but just one in the layer underneath. So I have broken the Z2 constraint for this yellow sublattice. And in both cases, when you do this, now I have an energy cost associated with creating defects with these boundary stabilizers. So it costs energy. So in the lattice model, I can only get, at least in this exactly solvable model, only get gapped boundaries. And once you put in the boundary, that also affects the kind of process that can happen when you bring your excitations to the boundary. So in this case, what we can move are dipoles. So imagine I start in the bulk and create 4 defects, but I take one pair of these defects of dipole to the boundary along this direction here, say in the YZ plane. And then because of this, now I have these stabilizers which violate the Z2 constraints, there is a process now that removes these excitations that live on these vertices here and create just one single defect at the boundary. So now we have this process that converts dipoles that come in from the bulk to a single fracton that lives at the boundary. So I call this the boundary fracton. And which kind of defect, which I'm painting by different colors according to those sublattice, which kinds I can convert depends on where we cut the surface. So for example, here it's for cutting at z equals 0. So I conserve, there is still a B here at the boundary, but I have completely erased the blue defect. If I move the boundary one layer below, now it's the other way around. So the kind of processes that convert dipoles to single fractons really depends on this information about the parity of this z coordinate where I put the boundary. And then, so we have at least these 2 types of gap boundaries that you can label by these boundary processes and the kinds of Z2 constraints that we violate. We'd like to understand this from the perspective of an effective field theory. And our starting point here is this theory that Wesley worked out with Pedro Gomez and Claudio. And it's a Chern-Simons-like action. It's an example of an effective field theory for Fracton systems. It's like Chern-Simons in the sense that you express your spin operators in terms of gauge fields. There's this index n here, so I need at least 2 gauge fields to represent the algebra of the spin operators. And notice that it's not really Chern-Simons because it's a different dimension. Here we're in 3+1. And also the spatial derivatives here are different. So this kind of theory involves second derivatives with respect to the coordinates, which are highly anisotropic. It depends on these directions. It has to do with the directions in which the dipoles propagate. But like Chern-Simons theory, the theory contains some kind of K-matrix which encodes the commutation relations, which is related to the algebra between the line operators that carry these excitations. And what we did on top of what Wesley had done before was to add a layer index, because now I want to distinguish between these different types of boundaries. So I have to carry this information, whether you're talking about planes with even and odd z. So I just add this upper index L here. And this theory has some gauge invariance, so you can transform your gauge fields like this. It looks like the standard gauge transformation, except that you have second derivatives here. And also, putting the factors of the lattice space in here, they really show up in the gauge transformation. And then we just went through the exercise of asking, now I have this kind of Church-Simons-like gauge theory. What if it has an open boundary? I put it in a geometry like this. And the steps here are very similar to the derivation of the Cairo edge states of the quantum Hall effect. Basically, you can show that having the boundary introduces a gauge anomaly, which forces you to interpret this in terms of some physical degrees of freedom that have to appear at the boundary. In practice, you can derive an effective action for the boundary by expressing the gauge fields in terms of derivatives, now second derivatives of a bosonic field, and then integrate the bulk action up to the boundary, and you get something now that only lives in 2+1 dimensions. So this is now written in terms of this bosonic field. It's a quadratic theory with the same K matrix that came from the bulk. And then there is this M matrix here, which carries the information about the dispersion, the dynamics of these boundary bosonic modes. And since it's a quadratic theory, you can go ahead and diagonalize this and calculate the spectrum. And because these are second derivatives, you get a dispersion relation, which is like this. It's quadratic, but highly anisotropic. And the dispersion actually vanishes along the directions where kx equals to plus or minus ky. So it vanishes along these lines. So this is already a signature of UV-IR mixing, because now you have these lines that extend out to arbitrarily large momentum. So you can have high momentum modes that contribute to the low energy physics, and then renormalization group kind of arguments become tricky in this kind of theory. So I mentioned the effective field theory predicts gapless boundary modes. So there is already a tension here between the field theory and the exactly solvable lattice model that I described before, where the boundaries were gapped. So to understand what's going on, we actually have to understand the kinds of symmetries that this effective field theory has. So first of all, it has a global U1 symmetry, so there is a conserved charge, which is now written like this in terms of the second derivatives of the bosonic field. And you can write down the operators that create charged excitations. These are exponentials of the bosonic field, which obey this kind of commutation relation. So a single explanation like this would just create one single defect, or a fracton, if you want to connect with the lattice model with these charges here. There's like a charge vector. If you want, you can also write down the operator that creates a pair of excitations. That would be the dipole of particles with opposite charges, and then you expand inside the exponential here. So it's now, if the dipoles has a very short separation, you get some exponential of the derivatives of the bosonic field. And the boundary action that I showed you before has actually more symmetries than the single global U1 symmetry. You can do this kind of local transformation where you shift the bosonic field by something that depends on the coordinates x plus or minus y. And these could be arbitrary functions which obey the condition that are actually annihilated by the second derivatives. So with this, you can like do a local transformation, U1 transformation, just along lines along these directions. And this has consequences for correlation functions. It implies that if you write down a correlation function for exponential of these bosonic fields, these charged operators, it can only be non-zero if you take at least 4 positions that live at the vertices of our rectangular membrane, because you basically have to cancel out all the phases that would come out from this transformation. So this is some kind of generalized neutrality condition by analogy with conformal field theory in lower dimensions. Another thing we checked from this understanding of creating charged excitations is that you can actually make sense of the boundary condition that we have to impose here. To derive the boundary action that I showed you before, we actually had to integrate the gauge fields all the way to the boundary, but the result depends on the direction in which you're integrating. And here we had this problem that you end up with some terms at the boundary that depend on the derivative of the bosonic field with respect to this normal direction, which here is the z direction. And to make sense of this in terms of the correct numbers of degrees of freedom matching between bulk and boundary, we had to impose this boundary condition that this normal derivative is actually has to be linearly dependent on the bosonic field itself. So some condition like this, where these coefficients would depend on the details of the boundary. But when you write down the operators that create excitations in the bulk and bring it all the way to the boundary now in the effective field theory, this kind of makes sense because you take this ribbon with this very narrow width, and you take it to the boundary at some position R0 here. Using this boundary condition, you can show that you end up with something at the boundary, which is just the exponential of the bosonic field itself and not the derivative. This means that this dipole that came from the boundary now becomes a single charged excitation. It becomes a fracton, like the process I described for the lattice model. By now, Eduardo should have realized that this looks very similar to the kind of thing we did during my master's, because this is very similar to bosonization. What we want to do now is to add some perturbations to this free boson theory that will gap out the degrees of freedom so we can recover gap boundaries for the Chamon model. When you add this kind of charge operators, they're bosonic explanations, the Hermitian operator would be like a cosine of this bosonic field that lives in 2+1 dimension. And if I can pin this bosonic field, I can generate a mass term which would look like this. But then the question is whether I can do this or not, pin this bosonic field to one of the minima of the cosine. And to figure out what would happen here, I had to remind myself of Eduardo's notes, introduction to bosonization, where you also have cosine operators, and you can figure out if they are relevant or irrelevant depending on the scaling dimensions of these operators. Oops. And to figure this out, the quick way is to compute correlation functions for these operators. That's what we did. And here there is some funny things going on. If you take, you can going to try and read out the scaling dimension from this correlation, because this theory is actually a scaling variant with dynamical exponent z equals 2, had to do with the quadratic dispersion I showed you. But it turns out that if you take just the correlation function for this two-point function for this exponential of the bosonic field, it's actually ultra short range. It vanishes for any choice of these two different positions, and that's because I had that constraint, the generalized neutrality condition, that I need at least 4 different points, a membrane, to cancel out the phases. So this one has really short range correlations, which means that this cosine of the bosonic field is actually irrelevant at weak coupling. But then you can actually go to the next step and ask about the effective scaling dimensions of the operators that create dipoles. Those are exponentials of the derivative of the bosonic fields. And these ones can have quasi-long range correlations that decay as power loss that depend on a lot of things, like parameters that appeared in the dispersion relation, but also these short range scales, like the width of the ribbon and some short distance cutoff. But as long as this exponent is small, that operator that you write here as a function of a cosine of derivative of the bosonic field can be a relevant operator, which is quite unusual because usually you think if you add more derivatives, the operators just become more irrelevant, but here it's the kind of the other way around. And when it's relevant, it can drive some kind of Kosterlitz-Thouless transition, take you away from this capless phase. But where it takes you is actually a non-fractonic phase, which you can understand just by the fact that if I try to expand this now, I generate terms which are like d phi squared, which just have a single derivative, so you kill the fractonic physics that was associated with second derivatives. And this kind of theory actually appeared before in two-dimensional models. There's like this XY plaquette model that was proposed back in 2002 for the, as some possible realization of a Bose metal. And this kind of theory has reappeared recently in the context of Fracton phases. We just happened to stumble upon this theory on the boundary of the Chamon model. And the way we reconcile the effective field theory with the lattice model is to think that actually the exactly solvable model is not in the weak coupling limit, it's at the strong coupling limit, because basically the excitations there are static, so they have no dispersion. And in this case, you can understand what's going on just by taking the cosine terms and neglecting the kinetic energy, and then there's only a transition between pinning one component of this bosonic field or the other, which would correspond to the two layers that I described before, right? And this would be a first order transition. We can back this up with some actually mapping this boundary of the Chamon model to some two-dimensional models, the quantum compass model on the square lattice of the Xu-Moore model, which are dual. But because we also found a gapless phase, now there is the question, this phase does not happen and does not occur in the lattice model, the exactly solvable model. So where is it? So we're currently trying to understand this gapless phase from a more microscopic perspective, and Claudio has been helping us with trying to realize these ideas. And with that, I'll just leave you with the conclusions, and thank you for your attention, and wish Eduardo a happy birthday.
Thanks for a nice talk. We have time for some questions before the coffee break.
Rodrigo, maybe this question is too broad, but there's that, we discussed that connection between fractons and elasticity theory, and that the immobile particles is the dislocation, right?
Yeah.
Is there any analog in the elasticity theory of what you're talking about in the case of how the dislocation will move to the surface when you of a crystal and so on, or this is not quite the same?
I have no idea. I haven't thought about that. There's probably some connection we should talk about. Yes, yes. Yeah, yeah.
Okay.
I don't know what happens when you put the boundary on this kind of theory. So.
Right. Yeah. I was just curious. Yeah.
Other questions? Okay, so maybe I have a very naive question. So when you look at the sort of defects moving in your toric code model, when they reach the edge, they sort of just, if they were allowed to leave, they left. You call that sort of condensation. Is there sort of any analogy? So like the analogy to your, so when you have these, dipoles that are moving and leaving a fracton at the edge, should I think of that as an analogy to when you're sort of leaving this edge on the mode, or to this condensation where it sort of disappeared? Yeah,
so here you don't have dipole condensation, right? That would also be a possibility. You bring the dipole all the way to the boundary and then it disappears. That kind of thing actually happens in the 001 boundary of the X cube. It's a different fractonic model, so that's already a difference from the Chamon model. Here, what process we have is this conversion of pairs of defects or single defects, but you can also think about it, if you like, as just condensing one of the single defects in the pair, right? So you just, but you cannot condense both on this boundary. So it's
okay. Thanks. Do we have any other questions? All right. If not, let's thank Rodrigo again. Now we have a coffee break, and then there's a poster session after the break.